Far beyond the warmth of the sun, where the golden glow gives way to the cold, dark expanse of space, a solitary planet drifts through the cosmic abyss. Neptune, the eighth and most distant planet in our solar system, lies shrouded in mystery. It is a place so remote that the sun appears as little more than a distant star, casting faint rays of light over a world unlike any other. Neptune's beauty is undeniable. Its vibrant blue hue captivates the imagination, a color so deep and serene that it evokes images of Earth's own oceans. But Neptune's azure face is no tranquil sea. Beneath its striking exterior lies an untamed world of extremes, where winds rage at unimaginable speeds and colossal storms churn relentlessly. It is a planet of paradoxes, a serene appearance masking an atmosphere of chaos, a distant, icy world that radiates unexpected heat from within, and a celestial body whose discovery was rooted in mathematics before it was ever glimpsed by the human eye. Let us begin with Neptune's most striking feature, its radiant blue color. This vivid shade, caused by methane in its atmosphere, sets it apart from every other planet in the solar system. Methane absorbs red light, leaving only the blue to scatter and shine back into the cosmos. It is a color that seems almost alive, pulsing against the inky blackness of space. Yet Neptune is not just a jewel for the eyes. It is a world filled with activity and mystery. Imagine standing on one of Neptune's moons, gazing out at the distant planet. From this vantage point, Neptune would appear as an immense glowing orb, its swirling storms faintly visible against its azure backdrop. Despite its distance, this planet pulses with energy. Winds there reach speeds of over 1,200 miles per hour, the fastest in the solar system. To put that in perspective, the strongest hurricanes on Earth barely exceed 200 miles per hour. Neptune's storms, like its famous Great Dark Spot, are colossal tempests that dwarf even the largest earthly hurricanes. They come and go unpredictably, forming and fading over weeks or months, in a dance of chaos and power. Neptune's remoteness fuels its mystique. It sits nearly 3 billion miles from the Sun, a staggering distance that makes it the last of the solar system's classical planets. At such a distance, sunlight takes over 4 hours to reach Neptune. The planet orbits in near darkness, completing a single trip around the Sun in 165 Earth years. This means that since its discovery in 1846, Neptune has completed just one orbit, with only a few decades into its second. But how did humanity discover this distant world? Unlike the other planets visible to the naked eye, Neptune was uncovered through the power of mathematics and observation. Astronomers in the 19th century noticed that Uranus, its neighboring planet, was behaving strangely, deviating from its predicted orbit. The gravitational pull of an unknown planet seemed to be the only explanation. French mathematician Urbain Le Verrier and British astronomer John Couch-Adams independently calculated where this mystery planet should be, leading to its eventual sighting by Johann Galle in 1846. Neptune's discovery marked a triumph of human intellect and determination, the first time a celestial body had been found by prediction rather than direct observation. But Neptune's story is more than its discovery. It is about what lies beneath its atmospheric veils. Unlike the gas giants Jupiter and Saturn, Neptune is classified as an ice giant. Its composition includes elements like water, ammonia, and methane, locked under crushing pressures that defy our understanding. Beneath its clouds, the temperatures and pressures are so extreme that these elements may exist in exotic states, with water forming superionic ice that behaves like both a solid and a liquid. Neptune's interior is still a mystery, one that tantalizes scientists and raises profound questions about how planets form and evolve in the cold reaches of space. Neptune also holds a special place as a gatekeeper. Beyond its orbit lies the Kuiper Belt, a region teeming with icy objects and dwarf planets, remnants of the solar system's earliest days. Neptune's immense gravity helps shape the orbits of these distant bodies, acting as a guardian of the outer solar system. It may even harbor secrets of its own, undiscovered moons, faint rings, or insights into the solar system's chaotic early history when the planets were still forming. For now, Neptune remains largely unexplored. Only one spacecraft, NASA's Voyager 2, has ever visited it, and that was over 30 years ago. In 1989, Voyager 2 captured the first close-up images of Neptune, revealing its dazzling blue surface, its faint rings, and its dynamic atmosphere. But this fleeting encounter only deepened the mystery. What other secrets lie hidden in the icy depths of this distant world? Imagine the vastness of space around Neptune, an expanse so cold and dark that it challenges the limits of our imagination. Picture the sun, so far away that it appears as a bright star among thousands. And there, floating in this cosmic void, is Neptune, glowing faintly with an enigmatic allure. It is a reminder of how much we have yet to learn, not just about our solar system, but about the universe itself. Neptune is more than just a planet. It is a symbol of human curiosity and the drive to explore. It beckons us to look beyond the familiar and into the unknown, to stretch the boundaries of what we know and discover what lies beyond. As we journey deeper into its story, we will uncover the incredible history of its discovery, the secrets of its powerful storms, the mysteries of its moons and rings, and the untold possibilities hidden within its icy heart. This is Neptune, the farthest world of the solar system, a planet of beauty, chaos, and endless mystery. A world that reminds us that no matter how far we go, there is always more to discover. The story of Neptune's discovery is one of the most remarkable tales in the history of astronomy. Unlike the planets visible to the naked eye, Neptune eluded direct observation for centuries. It was not found by chance, but rather by the power of mathematics and the determination of astronomers who sought to solve a celestial mystery. Our story begins in the early 19th century with the planet Uranus, the first planet discovered in the modern age. Astronomers had been tracking Uranus since its discovery in 1781, carefully mapping its orbit and predicting its path through the heavens. But something was wrong. Uranus wasn't following the path expected of it, as though an unseen hand was tugging at it from the void. These deviations puzzled astronomers for decades. Was the data wrong, or was there something else at play? By the mid-1800s, a new idea began to emerge. Perhaps Uranus's strange behavior was caused by the gravitational pull of another, yet-to-be-discovered planet. This notion sparked a race to find the mysterious celestial body that seemed to be lurking in the outer solar system. Enter two brilliant minds working independently of one another, Urbain Le Verrier in France and John Couch Adams in England. Both men set out to calculate the position of this hypothetical planet using only the laws of physics and mathematics. It was an audacious endeavor. They had to rely on Newton's law of gravitation to predict the orbit of a planet no one had ever seen, based solely on its gravitational influence on Uranus. In 1846, Urbain Le Verrier completed his calculations and sent his findings to the Berlin Observatory. Johann Gottfried Galle, an astronomer at the observatory, received Le Verrier's letter and decided to act on it immediately. On the very night of September 26, Galle pointed his telescope to the coordinates provided by Le Verrier, and there it was, a faint bluish disk in the sky. Neptune had been found, almost exactly where Le Verrier had predicted it would be. This moment was groundbreaking. It marked the first time in history that a planet had been discovered not through direct observation, but through theoretical prediction. Neptune's discovery was hailed as a triumph of human intellect, a testament to the power of science and mathematics to unveil the unseen. But this achievement wasn't without controversy. John Couch Adams, who had completed similar calculations in England, had independently predicted Neptune's position as well. However, due to delays in communication and missed opportunities, Adams's findings were not acted upon in time. This led to a heated debate over who truly deserved credit for Neptune's discovery. In the end, both Adams and Le Verrier are now recognized for their contributions, their combined efforts forever linked to this monumental discovery. The discovery of Neptune also revealed something profound about our solar system. It showed that our understanding of the cosmos was not limited to what we could see. Instead, by applying the principles of physics, we could uncover hidden truths about the universe, predicting the existence of worlds we had yet to observe. Neptune's discovery also underscored the power of collaboration in science. Though separated by distance and working independently, the efforts of Leverrier, Adams, and Gall converged to bring Neptune into the fold of known planets. Their work opened a new chapter in astronomy, inspiring future generations to look beyond what is visible and seek answers to the unknown. Imagine the moment when Gally and his assistant first glimpsed Neptune through their telescope, a tiny, faint point of light on the edge of the solar system, distant yet unmistakable. For them, it was not just a discovery of a new planet, but a glimpse into the boundless possibilities of science. Today, Neptune stands as a reminder of humanity's ability to solve the mysteries of the cosmos through ingenuity and persistence. It challenges us to think of what might still be out there, hidden in the vast expanse of space, waiting to be discovered. Just as Neptune was found by those who dared to imagine the unseen, what other wonders might we uncover as we continue to explore the universe? With the discovery of Neptune, we moved one step closer to understanding the structure and scale of our solar system. And as we delve deeper into its story, we'll see how this distant world has continued to captivate scientists and dreamers alike. Neptune resides at the outermost edge of the solar system, a solitary sentinel in the vast expanse of space. Orbiting at an average distance of 2.8 billion miles from the Sun, it is the eighth and final planet, marking the boundary between the known worlds and the distant, icy frontier of the Kuiper Belt. This distance is almost unimaginable. To put it in perspective, Neptune is about 30 times farther from the Sun than Earth. For comparison, if the Earth's orbit were the size of a standard dinner plate, Neptune's orbit would stretch nearly to the length of a football field. At this staggering distance, sunlight takes over 4 hours to reach Neptune's cloud tops, where it provides only a fraction of the warmth and light that bathes Earth. Neptune's orbit is a slow, stately journey. It takes 165 Earth years for Neptune to complete a single revolution around the Sun. This means that since its discovery in 1846, Neptune has completed just one orbit, and it is now well into its second. Imagine this. A single Neptunian year encompasses the entirety of modern human history since the mid-19th century. Despite its distance, Neptune's orbit is remarkably stable, governed by the same laws of gravity that keep all the planets in line. But its journey through the cosmos is not without intrigue. Neptune's presence plays a key role in shaping the outer regions of the solar system. Its gravitational pull influences the orbits of countless smaller objects in the Kuiper Belt, a region filled with icy remnants from the solar system's formation. Some of these objects are in orbital resonance with Neptune, meaning their movements are synchronized with the planet's orbit in a delicate cosmic dance. Yet Neptune's position in the solar system also represents a boundary. It is the last of the classical planets, the furthest world we can consider part of the Sun's immediate family. Beyond Neptune lies a realm of shadows between the Kuiper Belt, the scattered disk, and the Oort cloud, regions populated by icy bodies and distant comets. These areas remain largely unexplored, but Neptune's gravitational influence serves as a bridge between the known and the unknown. Interestingly, Neptune was not always alone in this distant part of the solar system. Theories about planetary migration suggest that during the early days of the solar system, Neptune and the other outer planets may have moved significantly from their original positions. Neptune's migration outward likely shaped the architecture of the Kuiper Belt, scattering some objects into stable orbits while ejecting others into interstellar space. This gravitational influence extends far beyond Neptune's immediate surroundings. For example, Neptune's orbit is closely tied to that of Pluto, the dwarf planet that occasionally crosses Neptune's path. Despite this, the two bodies will never collide, as their orbits are locked in a stable resonance, with Pluto completing 2 orbits for every 3 of Neptune's. Now, imagine what it would be like to visit Neptune and see the Sun from its vantage point. The Sun would no longer dominate the sky as it does on Earth. Instead, It would appear as a brilliant, distant point of light, casting a dim twilight over Neptune's cloud tops. The faint sunlight would barely warm the planet, leaving it in a perpetual state of frigid cold. But Neptune's position in the solar system isn't just about its distance from the Sun. It's also about its place in our understanding of planetary science. Neptune stands as a gateway to the study of ice giants, a category of planets distinct from the gas giants Jupiter and Saturn. Its unique position allows scientists to study how such planets form and evolve, particularly in regions where sunlight is weak and temperatures are extraordinarily low. Neptune's place in the solar system is a testament to its endurance and stability, quietly orbiting at the frontier of the Sun's influence. It holds clues to the solar system's past and future, acting as both a marker of its outer limits and a key to understanding the forces that shaped it. As we journey closer to Neptune in this exploration, we'll uncover its physical beauty, dynamic atmosphere, and the secrets hidden within its icy depths. For now, let us marvel at its position, a distant beacon of the unknown, reminding us of the vastness and complexity of the solar system we call home. From the depths of space, Neptune stands as one of the most visually captivating planets in the solar system. Its brilliant blue hue, so vivid and striking, sets it apart from every other planet. This color, caused by the methane in its atmosphere, reflects sunlight in a way that leaves an impression of serenity. Yet beneath this tranquil exterior lies a planet of immense power and mystery. Neptune is the fourth largest planet by diameter, measuring nearly 4.9244 kilometers across, almost 4 times the size of Earth. Yet its mass tells a more complex story. While it is the third most massive planet, its density is significantly higher than its closest sibling, Uranus. This difference hints at variations in their compositions and internal structures, offering clues to how Neptune may have formed in the early solar system. As you gaze at Neptune through a telescope, its surface appears smooth and unbroken, a canvas of unchanging blue. But a closer look reveals subtle features, faint bands and shadowy spots that tell a story of dynamic activity beneath the clouds. One of the most remarkable discoveries made by Voyager 2 during its flyby in 1989 was Neptune's Great Dark Spot, a massive storm system similar to Jupiter's Great Red Spot. This storm, larger than Earth, appeared as a dark oval against the planet's vibrant blue. Unlike Jupiter's persistent Great Red Spot, Neptune's storms are transient. The Great Dark Spot observed by Voyager 2 had vanished just a few years later when the Hubble Space Telescope turned its gaze toward Neptune. In its place, new storms had formed, revealing the ever-changing nature of the planet's atmosphere. The texture of Neptune's appearance goes beyond its storms. High-altitude clouds of frozen methane crystals drift through the atmosphere, casting soft shadows over the planet. These clouds often gather around the planet's equator and poles, creating a layered, three-dimensional effect when observed from afar. Beneath its swirling clouds lies a world we can only imagine. Neptune has no solid surface. Instead, its visible surface is the top of a thick atmosphere that extends deep into the planet's interior. This atmosphere gradually transitions into a dense, slushy layer of water, ammonia, and methane, the materials that define Neptune as an ice giant. Neptune's physical appearance also speaks to its dynamic energy. Despite being nearly 3 billion miles from the Sun, Neptune radiates more heat into space than it receives. This internal heat drives its violent weather systems, fueling the storms and high-speed winds that shape its atmosphere. Imagine standing on a hypothetical platform floating above Neptune's cloud tops. The deep blue would stretch endlessly in every direction, with wispy white clouds streaking across the horizon. In the distance, faint shadows of storms could be seen swirling, their immense scale both awe-inspiring and humbling. Above, the sun would appear as a tiny, distant star, casting a dim, cold light over the entire scene. From Earth, Neptune's visual beauty offers only a glimpse of its complexity. Its radiant blue color has inspired countless comparisons to our own oceans, even earning it the name of the Roman god of the sea. But its true nature is far more extreme, a world shaped by forces we can barely comprehend, with an appearance that captures the imagination while hiding its deeper secrets. Neptune's physical characteristics also make it a cornerstone of scientific study. Its size, mass, and density challenge our understanding of planetary formation and composition. The contrast between Neptune's dynamic atmosphere and its icy, slushy interior offers a unique opportunity to study the behavior of materials under extreme conditions, helping scientists refine models of how planets form, not just in our solar system, but around other stars as well. And yet, for all its beauty, Neptune remains a distant enigma. Even the most advanced telescopes struggle to reveal its finer details from Earth. The images captured by Voyager 2, though revolutionary, are just snapshots of a planet that continues to change and evolve. What lies beneath its blue expanse? How do its storms form and dissipate so quickly? And what mysteries are locked within its icy core? Neptune's appearance is a reflection of its character, at once calm and chaotic, simple yet profoundly complex. It is a reminder that even in the vastness of space, beauty and mystery often go hand in hand. As we delve deeper into Neptune's story, we'll uncover the forces that shape its atmosphere, the secrets of its internal structure, and the incredible dynamics that make it one of the most fascinating planets in the solar system. For now, let us marvel at its physical form, a glowing beacon of blue on the edge of the solar system, calling us to explore further. Neptune's atmosphere is one of the most tumultuous and extreme environments in the solar system, a realm of endless motion and raw power. It is an atmosphere that seems alive, constantly shifting, with storms forming and dissipating in a cosmic heartbeat. From its icy blue exterior to its violent winds, Neptune's atmosphere tells a story of a world shaped by energy and chaos. At first glance, Neptune's atmosphere appears serene, a calm expanse of vivid blue. But hidden within this tranquil facade are some of the fastest winds and most intense weather systems ever observed. These winds can reach speeds of up to 1,200 miles per hour, nearly 5 times faster than the strongest hurricanes on Earth. To put this into perspective, at such speeds, Neptune's winds could circle the entire Earth in just 16 hours. The forces driving these winds are still a mystery. Neptune receives only a fraction of the sunlight that Earth does, meaning its atmosphere isn't powered by solar energy in the same way. Instead, scientists believe Neptune's winds are fueled by heat from within the planet. This internal heat, radiated outward from Neptune's core, creates convection currents in the atmosphere, driving the ferocious winds and weather patterns that define this icy giant. One of the most remarkable features of Neptune's atmosphere is its storms. These massive tempests appear as dark spots against the planet's blue surface, earning comparisons to Jupiter's iconic Great Red Spot. The most famous of these, the Great Dark Spot, was discovered during Voyager 2's historic flyby in 1989. This immense storm was large enough to fit Earth inside it, with winds roaring at over 700 miles per hour. Yet, unlike Jupiter's Great Red Spot, which has persisted for centuries, Neptune's storms are fleeting. When the Hubble Space Telescope observed Neptune just a few years after Voyager 2, the Great Dark Spot had vanished, replaced by other, smaller storms. This rapid formation and dissipation of storms is a hallmark of Neptune's atmosphere, a sign of its dynamic and ever-changing nature. Accompanying these storms are high-altitude clouds, composed of frozen methane crystals. These clouds often appear as bright streaks or clumps in Neptune's atmosphere, casting delicate shadows on the planet's lower layers. They can stretch for thousands of miles, drifting with the winds and providing further evidence of the atmosphere's complexity. But Neptune's storms and winds are not the only sources of intrigue. Its atmosphere is also home to an unusual phenomenon known as superrotation. This occurs when Neptune's equatorial winds travel faster than the planet's rotation, creating a banded structure similar to what we see on other gas and ice giants. These bands, though faint and difficult to observe, reveal the underlying forces shaping Neptune's weather systems. Neptune's upper atmosphere is primarily composed of hydrogen and helium, with traces of methane that give the planet its iconic blue color. But as you descend deeper into the atmosphere, the pressure and temperature increase dramatically. Here, the simple molecules of methane, ammonia, and water begin to behave in ways we can scarcely imagine, forming exotic materials that may hold the key to understanding the planet's interior. The extremes of Neptune's atmosphere also make it a laboratory for studying weather patterns and fluid dynamics on a scale impossible to replicate on Earth. Scientists are fascinated by how such intense winds and storms can exist in a region so far from the Sun, where temperatures plunge to -220 degrees Celsius. The answers lie in Neptune's unique balance of internal heat, atmospheric composition, and the rotation of the planet itself. Imagine standing on a platform suspended in Neptune's upper atmosphere. Around you, the winds roar with an unrelenting fury, carrying frozen methane crystals in swirling, chaotic patterns. The blue expanse stretches endlessly, punctuated by the faint outlines of massive storms in the distance. The light is dim, a perpetual twilight created by the faint glow of the distant sun. Here, in this alien world of extremes, you would witness weather on a scale unlike anything on Earth, a reminder of the sheer power and beauty of the universe. Neptune's dynamic atmosphere is not just a spectacle, it is a mystery. How does a planet so far from the Sun generate such energy? What processes sustain its ferocious winds and fleeting storms? And what secrets lie hidden beneath the clouds, in the depths where the atmosphere transitions into the icy mantle? These questions drive our fascination with Neptune and its atmosphere. As we continue to study this distant world, we are not only learning about the planet itself, but also uncovering broader truths about the forces that shape planets, weather, and the cosmos. Neptune's atmosphere is a dance of chaos and beauty, a reminder that even in the cold, distant reaches of space, energy and motion thrive. And as we move deeper into the story of this icy giant, we'll explore the frigid temperatures, internal heat, and mysterious processes that make Neptune one of the most fascinating planets in the solar system. Neptune is a planet of extremes, where the interplay of its frigid temperatures and mysterious internal heat creates one of the most dynamic climates in the solar system. Sitting nearly 3 billion miles from the Sun, Neptune's environment is shaped by a profound cold, yet paradoxically driven by unseen warmth emanating from within. This duality defines the planet, making it a fascinating enigma for scientists and dreamers alike. At first glance, Neptune appears to be a frozen world. Its distance from the Sun means it receives only a fraction of the sunlight that reaches Earth. On its cloud tops, temperatures plummet to a staggering 1,220 degrees Celsius, making it one of the coldest places in the solar system. To imagine such cold is almost beyond comprehension. At these temperatures, the atmosphere's methane freezes into delicate ice crystals, forming the faint, wispy clouds we see drifting across Neptune's surface. But while the icy cold dominates its outer layers, Neptune harbors an unexpected secret. It radiates more than twice as much energy into space as it receives from the Sun. This internal heat, generated deep within the planet, powers the violent storms and roaring winds that define its atmosphere. The source of this internal heat remains one of the great mysteries of planetary science. Neptune, like its sibling Uranus, is classified as an ice giant. Its interior is believed to consist of a dense core of rock and metal, surrounded by a thick mantle of water, ammonia, and methane. Under the immense pressures found in Neptune's depths, these elements may exist in exotic states, such as superionic ice, where water behaves as both a solid and a liquid. This internal structure is thought to play a key role in generating Neptune's heat. As the planet slowly cools over billions of years, the heat from its formation may still be escaping into space. Additionally, friction between layers within Neptune's mantle could be generating extra energy, though the exact mechanisms remain a topic of ongoing research. This internal heat is not just a curious detail, it drives the planet's entire climate system. The heat rises through the atmosphere, creating powerful convection currents that fuel Neptune's storms and high-speed winds. These winds, the fastest in the solar system, roar at speeds of over 1,200 miles per hour, shaping the planet's bands and spots. Neptune's dual nature, frigidly cold on the outside, yet warm and energetic within, creates a climate that is both extreme and unique. The stark temperature differences between its upper atmosphere and its deeper layers lead to turbulent weather patterns. This turbulence is most visible in Neptune's storms, such as the Great Dark Spot observed by Voyager 2. These immense tempests form, grow, and dissipate rapidly, their life cycles driven by the dynamic energy coursing through the atmosphere. Imagine what it would be like to experience Neptune's climate firsthand. If you were to descend through its atmosphere, you would begin in the icy outer layers, where methane crystals form clouds against a deep blue sky. As you move deeper, the temperatures and pressures would increase, and the cold would give way to an environment dominated by energy and heat. In these depths, the atmosphere transitions into a slushy ocean of exotic materials, a place where the concepts of solid, liquid, and gas blur into something alien. Despite its distance from the sun, Neptune's internal heat creates an active and vibrant world. This heat challenges our understanding of how planets work. Why does Neptune radiate so much energy, while its sibling Uranus, nearly identical in size and composition, appears far less active? What processes sustain this heat after billions of years? These are questions that continue to puzzle scientists, driving our desire to study this distant world further. Neptune's temperature and climate also have implications beyond the planet itself. By studying how heat moves through Neptune's atmosphere, scientists can refine models of weather and climate that apply not just to our solar system, but to exoplanets orbiting other stars. The insights we gain from Neptune may one day help us understand the diverse worlds scattered across the galaxy. Neptune's extremes, its icy temperatures, and internal heat are a reminder that the universe often defies our expectations. Even in the coldest, most distant reaches of the solar system, energy and motion thrive. This contrast between cold and heat, chaos and serenity, makes Neptune a world of endless fascination. As we continue our journey through Neptune's story, we'll explore its unique composition, its mysterious magnetosphere, and the moons and rings that orbit this icy giant. For now, let us marvel at its climate, a delicate balance of extremes that reveals the beauty and complexity of this faraway world. Beneath its dynamic atmosphere, Neptune hides a world of extraordinary complexity. Its composition and structure set it apart from the gas giants, placing it in a unique category of planets known as ice giants. Understanding Neptune's internal makeup reveals not only the planet's secrets, but also the broader story of planetary formation in the far reaches of the solar system. Neptune, like its sibling Uranus, is composed primarily of hydrogen and helium, with traces of methane in its upper atmosphere. This methane is responsible for Neptune's vivid blue color, as it absorbs red light and scatters blue. But this outer layer is merely the surface of a much deeper and more enigmatic world. Beneath the atmosphere lies Neptune's mantle, a vast region unlike anything we find on Earth. This mantle is composed of water, ammonia, and methane, materials that remain stable as ices under the extreme pressures and low temperatures of the outer solar system. However, as you descend deeper into Neptune, these materials encounter conditions so intense that they transform into exotic states of matter. Scientists believe that the high pressures within Neptune's mantle could create superionic ice, a strange form of water that behaves like both a solid and a liquid. In this state, oxygen atoms remain locked in a lattice structure, while hydrogen ions flow freely through the lattice, conducting electricity. This superionic ice could be one of the keys to understanding Neptune's unusual magnetic field, which we'll explore in greater detail later. At the heart of Neptune lies its core, a dense region of rock and metal likely similar in composition to Earth's core but much larger. This core is thought to be surrounded by a layer of molten, electrically conductive materials that generate Neptune's internal heat. This heat radiates outward, powering the storms and winds that rage across Neptune's atmosphere. One of the most intriguing aspects of Neptune's structure is the transition from its gaseous atmosphere to its icy mantle. Unlike the gas giants Jupiter and Saturn, which are primarily hydrogen and helium, Neptune's atmosphere gradually thickens and compresses into a supercritical fluid state where distinctions between gas and liquid disappear. This fluid layer blends seamlessly into the mantle, creating a boundary that is difficult to define. Neptune's unique structure raises profound questions about how ice giants form and evolve. Unlike gas giants, which are thought to have formed quickly by accreting hydrogen and helium from the solar system's early disk, ice giants like Neptune may have formed more slowly, accumulating heavier elements like water, ammonia, and methane before the lighter gases were swept away. This slower formation process could explain why Neptune's composition is so different from that of Jupiter and Saturn. Despite its classification as an ice giant, Neptune's composition hints at a world that is anything but static. The exotic materials within its mantle and the high pressures at its core create conditions that are still poorly understood. Scientists believe that diamonds may form deep within Neptune's mantle, where the intense pressure causes methane molecules to break apart, freeing carbon atoms that crystallize into diamonds. These diamonds could slowly sink toward the planet's core, creating a diamond rain that adds to the mystery of Neptune's interior. Neptune's structure also provides clues about its origins. The presence of heavier elements suggests that it formed in a region of the solar system rich in icy materials, possibly closer to the Sun before migrating outward to its current position. This migration would have been a chaotic process, shaped by gravitational interactions with other planets and the surrounding disk of debris. Imagine descending into Neptune's interior. At first, you'd encounter the swirling winds and clouds of its upper atmosphere, but as you sank deeper, the atmosphere would thicken, pressing against you with unimaginable force. The temperature would rise, and the gases would transition into a slushy, supercritical fluid. Further down, the fluid would give way to a strange, hot ocean of exotic ices, glowing faintly from the planet's internal heat. At the very center lies Neptune's dense, rocky core, shrouded in layers of mystery and immense pressure. This journey through Neptune's structure underscores the challenges of exploring such a distant world. The extreme pressures and temperatures within Neptune make direct study impossible with current technology. Instead, scientists rely on theoretical models, laboratory experiments, and the brief data collected by Voyager 2 to piece together a picture of what lies beneath its clouds. Neptune's composition and structure are a testament to the diversity of planets in our solar system. While it shares some characteristics with Uranus, its unique features, such as its intense internal heat and dynamic atmosphere, set it apart, offering a glimpse into the variety of planetary systems that may exist throughout the galaxy. As we continue our journey, we'll explore Neptune's magnetic field, its faint yet fascinating rings and its moons, which offer additional layers of insight into this distant, enigmatic world. For now, let us marvel at its composition, a complex and beautiful interplay of ice, gas, and energy that makes Neptune one of the most fascinating planets in the solar system. Neptune's magnetic field is a phenomenon that challenges our understanding of planetary science. Unlike Earth's magnetic field, which aligns closely with its rotational axis, Neptune's magnetic field is a puzzle, tilted and offset in ways that defy easy explanation. This magnetic quirk is one of the most intriguing aspects of the ice giant, revealing a dynamic and complex interior. At first glance, Neptune's magnetic field might seem ordinary. It shields the planet from the solar wind, a constant stream of charged particles emitted by the sun. But a closer look reveals its unusual nature. Neptune's magnetic field is tilted by 47 degrees relative to its axis of rotation, and is significantly offset from the planet's center. This means that the magnetic poles do not line up with the geographic poles, and the field itself is lopsided, with one end closer to the surface than the other. The source of Neptune's magnetic field lies deep within its interior. Unlike Earth, where the magnetic field is generated by the motion of molten iron in its core, Neptune's field is thought to arise from a layer of electrically conductive materials within its mantle. This layer, composed of water, ammonia, and methane under extreme pressures, may create conditions where ions move freely, generating the planet's magnetic field. But why is Neptune's field so irregular? Scientists believe the answer lies in the unique structure of its interior. Unlike the gas giants Jupiter and Saturn, which have relatively uniform layers of hydrogen and helium, Neptune's interior is more complex, with varying regions of density and composition. These irregularities may disrupt the flow of electrically charged materials, leading to the tilted and offset field we observe today. Neptune's magnetic field also has fascinating implications for its auroras and light display similar to Earth's northern and southern lights. On Earth, auroras occur when charged particles from the solar wind are funneled along magnetic field lines to the poles, where they collide with the atmosphere and release energy as light. On Neptune, however, the magnetic fields tilt and offset, create auroras that are uneven and unpredictable, appearing at different latitudes rather than strictly at the poles. Imagine standing on one of Neptune's moons, looking down at the planet as faint auroras dance across its surface. The display would be unlike anything seen on Earth, with shimmering lights tracing the lines of an asymmetric magnetic field, a visual testament to the planet's dynamic interior. Neptune's magnetosphere also interacts with its rings and moons in unique ways. The charged particles trapped within the magnetosphere can affect the composition and structure of the planet's faint rings, creating subtle variations that hint at the forces at play in this distant world. Similarly, Neptune's moons, particularly Triton, may influence the magnetosphere, adding another layer of complexity to the system. The study of Neptune's magnetic field is more than just an exploration of the planet itself. It provides valuable insights into the nature of magnetic fields throughout the cosmos. By comparing Neptune's field to those of other planets, scientists can refine their models of how magnetic fields form and evolve, shedding light on the behavior of exoplanets and their potential to support life. Neptune's magnetic field was first revealed during Voyager 2's historic flyby in 1989. The spacecraft's instruments detected the tilt and offset, providing the first glimpse of this unusual phenomenon. Since then, scientists have relied on theoretical models and computer simulations to study the field, as no other spacecraft has visited Neptune to gather additional data. This lack of direct observation underscores the challenges of studying Neptune's magnetosphere. Its vast distance from Earth makes it difficult to explore, and the complexity of its magnetic field requires sophisticated models to interpret. Yet, these challenges also highlight the importance of Neptune as a target for future missions. A dedicated spacecraft equipped with modern instruments could provide new insights into the planet's interior, its magnetic field, and the processes that sustain it. Imagine the discoveries waiting to be made. By probing Neptune's magnetic field, we could uncover clues about the planet's formation, its interior structure, and the behavior of magnetic fields in other parts of the galaxy. We might even learn something about Earth's own magnetic field by studying how Neptune's differs and what drives those differences. Neptune's magnetosphere is a reminder that even in the farthest reaches of the solar system, there is still so much to learn. Its tilted, lopsided field challenges our understanding of planetary dynamics and invites us to explore further. As we continue our journey, we'll shift our focus outward to Neptune's moons and rings, where more mysteries and marvels await. For now, let us reflect on its magnetic field, a dynamic and enigmatic force that shapes the planet and its surroundings in ways we are only beginning to understand. Orbiting Neptune is a fascinating collection of moons, each with its own story to tell. Among these, Triton stands out as the crown jewel, a celestial body so unique and mysterious that it has reshaped our understanding of planetary systems. Alongside Triton, Neptune's smaller moons add depth to the narrative of this distant planet, revealing insights into its past and its dynamic present. Neptune has 14 known moons, ranging from tiny, irregularly shaped objects to the massive and enigmatic Triton. These moons are a diverse group, each one offering a glimpse into the processes that shaped Neptune's corner of the solar system. Triton, Neptune's largest moon, dominates the system. It is a world unlike any other, with features that make it as fascinating as Neptune itself. Triton is slightly smaller than Earth's moon, yet its surface is a patchwork of icy plains, frozen lakes, and geysers that spew nitrogen gas into space. These geysers are driven by heat from beneath Triton's surface, possibly from radioactive decay or tidal forces caused by its orbit around Neptune. What sets Triton apart from every other major moon in the solar system is its retrograde orbit. It moves around Neptune in the opposite direction of the planet's rotation. This unusual motion suggests that Triton did not form alongside Neptune, but was instead a captured object, likely originating from the Kuiper Belt, a distant region of icy bodies beyond Neptune's orbit. The capture of Triton was a violent event, one that likely disrupted Neptune's original system of moons. The gravitational interactions that brought Triton into orbit around Neptune would have ejected many of the planet's early moons into space. Over time, Triton's orbit circularized, but the scars of its tumultuous past remain in its retrograde motion and its unusual composition. Imagine standing on Triton's icy surface. The landscape would be alien and stark, with frozen nitrogen stretching to the horizon, broken only by cracks and ridges formed by geologic activity. In the faint sky above, Neptune would loom large, its deep blue color casting an eerie light over the frozen terrain. Beyond Triton, Neptune's other moons tell quieter but equally intriguing stories. Proteus, the second largest moon, is irregularly shaped and heavily cratered, resembling a giant asteroid. It orbits close to Neptune and is thought to be a remnant of the planet's original satellite system. Nereid, another of Neptune's moons, has one of the most eccentric orbits in the solar system. It moves in a highly elongated path, taking it far from Neptune at its most distant point. This orbit suggests that Nereid, like Triton, may have been affected by Neptune's chaotic early history, its path shaped by gravitational interactions with the planet and its other moons. The smaller moons, such as Naiad, Thalassa, and Despina, orbit closer to Neptune, nestled within the planet's ring system. These moons are tiny and irregular, likely formed from debris left over after the planet captured Triton. Their close proximity to Neptune means they are constantly interacting with the planet's gravity and its rings, creating a complex dance of motion and forces. One of the most intriguing mysteries surrounding Neptune's moons is the possibility of undiscovered satellites. With the current tally at 14, it is likely that more moons, especially smaller or distant ones, remain hidden in the vastness of space. Future missions to Neptune could reveal new moons, expanding our understanding of the planet's gravitational influence and its role in the outer solar system. Triton, however, remains the centerpiece of scientific interest. Its icy surface, active geysers, and retrograde orbit make it a prime candidate for future exploration. Scientists speculate that Triton may harbor a subsurface ocean beneath its frozen crust, kept liquid by the heat generated from tidal forces. If such an ocean exists, it could be a potential habitat for microbial life, making Triton one of the most exciting targets for astrobiology in the solar system. The study of Neptune's moons provides a window into the planet's history and its interactions with the Kuiper Belt. Triton, as a captured object, offers clues about the processes that govern planetary migration and the evolution of satellite systems. The smaller moons, meanwhile, reflect the remnants of a system shaped by gravitational chaos, a testament to the dynamic forces at play in the early solar system. As we continue to explore Neptune's story, its moons remind us of the diversity and complexity of the worlds that orbit our Sun. Each moon, from Triton's icy plains to Proteus's cratered surface, adds a chapter to the narrative of this distant planet. Next, we'll shift our focus to Neptune's rings, a faint and fragile system that complements the planet's mysterious beauty. For now, let us marvel at the moons of Neptune, each one a tiny world with a story waiting to be told. Encircling Neptune is a delicate and elusive system of rings, faint structures that add a subtle grace to this distant world. While they may lack the grandeur of Saturn's brilliant rings, Neptune's rings possess their own quiet beauty, whispering secrets of their formation and the forces that sustain them. Neptune's rings were first hinted at in the mid-20th century, when astronomers observed stars briefly dimming as they passed behind the planet. These dimming events suggested the presence of partial rings or arcs, It wasn't until Voyager 2's flyby in 1989 that the true nature of Neptune's rings was revealed. The spacecraft captured detailed images of these faint, fragmented structures, confirming that Neptune has a ring system of its own, composed of dark particles that barely reflect light. Unlike the broad, continuous rings of Saturn, Neptune's rings are narrow and clumpy, with sections appearing brighter than others. This uneven distribution creates a sense of impermanence, as if the rings are still in the process of forming or eroding. The rings are named after astronomers who contributed to the study of Neptune: Adams, Leverrier, Lassell, Arago, and Galilei. One of the most intriguing aspects of Neptune's rings is their composition. They are made primarily of microscopic particles of dust, mixed with larger fragments of ice and rock. These particles are coated with a dark material, possibly organic compounds altered by radiation from the sun. This gives the rings their dim, reddish appearance, a stark contrast to the bright, icy rings of Saturn. The origins of Neptune's rings remain a mystery. One theory suggests that they formed from debris left over after the capture of Triton, Neptune's largest moon. The gravitational chaos caused by Triton's arrival could have shattered smaller moons or asteroids, creating a disk of material that eventually coalesced into rings. Another possibility is that the rings are the remnants of a moon that was torn apart by Neptune's tidal forces, its fragments gradually spreading out to form the structures we see today. Neptune's rings are also notable for their arcs, localized clumps of material that appear to defy the natural tendency of ring particles to spread out evenly. These arcs are found within the outermost ring atoms and are thought to be stabilized by the gravitational influence of nearby moons. For example, the moon Galatea orbits just inside the atom's ring and may act as a shepherd, using its gravity to keep the arcs confined and prevent them from dispersing. This interaction between Neptune's rings and its moons is a delicate dance, one that highlights the dynamic nature of the planet's environment. The arcs, with names like Liberté, Égalité, and Fraternité, are particularly intriguing because they challenge our understanding of how ring systems evolve over time without the influence of shepherd moons. These arcs would likely dissipate within a few thousand years. Yet they persist, a testament to the complex gravitational relationships within Neptune's system. Imagine standing on a hypothetical platform near Neptune, gazing at its rings through the dim light of the distant sun. The rings would appear as faint, ghostly bands encircling the planet, their uneven brightness creating a fragmented, almost ethereal effect. Nearby, tiny moons like Galatea would move silently through the void, their orbits intertwined with the rings they help to shape. Neptune's ring system also raises questions about its longevity. Because the rings are composed of small particles that can be eroded by micrometeoroid impacts or dragged inward by Neptune's gravity, they are likely short-lived on a cosmic timescale. This suggests that the rings we see today may be relatively young, formed in the recent past by a specific event, such as a collision or the breakup of a moon. Despite their faintness, Neptune's rings provide valuable insights into the processes that govern planetary ring systems. By studying these delicate structures, scientists can learn more about how rings form, how they interact with moons, and how they evolve over time. These lessons extend beyond Neptune, offering clues about the rings of other planets and even the disks of material that surround young stars. The rings of Neptune are a reminder that even in the farthest reaches of the solar system, beauty and complexity abound. Their fragile appearance belies the intricate forces that sustain them, forces that connect them to Neptune's moons and the planet itself. As we continue our journey, we'll explore the exploration of Neptune and the challenges of studying such a distant world. But for now, let us marvel at its rings, faint and fleeting, yet profoundly significant, a subtle adornment to one of the most mysterious planets in the solar system. The exploration of Neptune represents one of humanity's greatest challenges, as the planet's incredible distance from Earth places it at the very edge of our technological and logistical capabilities. Despite these challenges, our brief encounter with Neptune, through the flyby of Voyager 2, provided a wealth of knowledge and unveiled the planet's remarkable beauty and complexity. Neptune lies nearly 30 times farther from the Sun than Earth, at an average distance of 4.3 billion kilometers. This immense separation means that light itself takes over 4 hours to travel from the Sun to Neptune, and signals from Earth would take the same amount of time to reach a spacecraft orbiting the planet. This makes real-time communication and navigation exceedingly difficult, adding to the complexity of exploring this distant world. To date, Voyager 2 remains the only spacecraft to have visited Neptune. Launched in 1977 as part of NASA's ambitious Voyager program, the spacecraft's journey to Neptune was a feat of engineering and ingenuity. After exploring Jupiter, Saturn, and Uranus, Voyager 2 reached Neptune on August 25, 1989, completing its grand tour of the outer planets. The flyby provided humanity with its first close-up images of Neptune, revealing the planet's vivid blue color, dynamic atmosphere, and faint ring system. Voyager 2 also discovered 6 new moons and observed the largest storm ever recorded on Neptune, the Great Dark Spot. These discoveries transformed our understanding of the planet, providing insights that continue to shape planetary science today. Voyager 2's encounter with Neptune lasted only a few hours, yet the data it collected was groundbreaking. Scientists were astonished by the planet's powerful winds, the fastest in the solar system, and its dynamic weather systems, including transient storms and high-altitude clouds. The spacecraft also confirmed the existence of Neptune's magnetic field, which is unusually tilted and offset, hinting at a complex and layered interior. Despite the wealth of knowledge gained from Voyager 2, it also highlighted how much we still don't know about Neptune. The flyby provided only a fleeting glimpse of the planet and its moons, leaving many questions unanswered. For example, the structure and composition of Neptune's interior remain largely theoretical, as do the processes driving its internal heat and dynamic atmosphere. Triton, Neptune's largest moon, was another focus of Voyager 2's exploration. The spacecraft revealed Triton's retrograde orbit, active geysers, and icy surface, sparking speculation about the possibility of a subsurface ocean. Yet much of Triton remains unexplored, and its potential as a habitat for life is one of the most compelling reasons to return to Neptune. The challenges of sending another mission to Neptune are immense. The journey would take at least 12 years, even with the assistance of gravity boosts from other planets. A spacecraft would need to carry advanced instruments capable of withstanding the extreme conditions of the outer solar system, as well as enough power to operate far from the Sun. Most current missions rely on solar panels for energy, but at Neptune's distance, sunlight is too weak to be practical. Instead, any future mission would likely use nuclear power, as Voyager 2 did. Despite these challenges, there is growing interest in returning to Neptune. A dedicated orbiter could provide long-term observations of the planet's atmosphere, magnetic field, and moons, building on the discoveries of Voyager 2. Such a mission could also study Neptune's rings in greater detail and search for additional moons that may remain hidden in the vastness of space. One of the most exciting possibilities is a lander or probe designed to explore Triton. By studying its surface and atmosphere up close, scientists could determine whether Triton's interior harbors liquid water and whether conditions there could support microbial life. Such a mission would not only deepen our understanding of Neptune, but also provide critical insights into the potential habitability of icy moons throughout the solar system. Imagine the discoveries waiting to be made by a new generation of explorers. A spacecraft orbiting Neptune could observe the planet's dynamic weather systems in real time, capturing the formation and dissipation of storms that dwarf anything seen on Earth. It could map Neptune's magnetic field with unprecedented precision, revealing the hidden layers of the planet's interior. And it could study the faint arcs within Neptune's rings, unraveling the mysteries of their origin and evolution. Neptune is not just a target for exploration, it is a window into the processes that shape planetary systems. By studying Neptune, we can learn more about the formation of ice giants, the behavior of extreme atmospheres, and the interactions between planets, moons, and rings. These lessons extend beyond our solar system, providing clues about the countless exoplanets orbiting distant stars. As humanity continues to push the boundaries of exploration, Neptune remains a frontier waiting to be rediscovered. Its distance may be daunting, but the rewards of studying this distant world are immeasurable. Voyager 2's brief encounter showed us the potential for discovery, and future missions promise to unlock even greater mysteries. As we continue our journey through Neptune's story, we'll explore its role in the broader solar system and the cultural and scientific significance it holds. For now, let us reflect on the challenges and triumphs of exploring this icy giant, a reminder of humanity's endless curiosity and drive to understand the cosmos. Neptune occupies a unique position in the solar system, not just as its most distant planet, but as a dynamic player in the intricate gravitational ballet that defines our cosmic neighborhood. Its influence extends far beyond its orbit, shaping the movements of celestial bodies and revealing the complexity of our solar system's outer reaches. At nearly 4.5 billion kilometers from the Sun, Neptune marks the outer boundary of the classical planets, standing as a gatekeeper to the vast Kuiper Belt AA region filled with icy remnants from the solar system's formation. This belt, stretching beyond Neptune, contains countless small objects, from dwarf planets like Pluto to comets that occasionally venture into the inner solar system. Neptune's immense gravity plays a crucial role in shaping this region, orchestrating the motions of these icy bodies through a phenomenon known as orbital resonance. Orbital resonance occurs when the gravitational influence of a planet synchronizes the orbits of smaller objects, creating stable patterns over time. Many Kuiper Belt objects, including Pluto, are in resonant orbits with Neptune. For example, Pluto completes 2 orbits around the Sun for every 3 orbits of Neptune, a 203 resonance that ensures their paths never cross, despite their close proximity. This delicate balance highlights Neptune's role as a stabilizing force in the chaotic outer solar system. Neptune's influence also extends to the scattered disk, a region of the solar system that overlaps with the Kuiper Belt but contains objects in more elongated and tilted orbits. These objects, such as the dwarf planet Eris, are thought to have been ejected into their current positions by Neptune's migration early in the solar system's history. This idea of planetary migration is central to understanding Neptune's role in shaping the solar system. Billions of years ago, during the solar system's formative period, Neptune and the other outer planets did not occupy their current orbits. Instead, they migrated outward, interacting with the surrounding disk of gas, dust, and small icy bodies. As Neptune moved outward, its gravity scattered countless objects, some of which were ejected into interstellar space, while others were captured into stable orbits in the Kuiper Belt. This migration also influenced the orbits of the other planets, contributing to the overall architecture of the solar system. Neptune's gravitational reach is immense, but its role is not limited to shaping the orbits of distant objects. It also serves as a barrier of sorts, preventing some comets from venturing into the inner solar system. These icy visitors from the Kuiper Belt and Oort cloud are often deflected by Neptune's gravity, either sending them into interstellar space or placing them into elongated orbits that keep them far from the Sun. But Neptune's role is not solely one of control. It is also a gateway to discovery. By studying Neptune and the objects influenced by its gravity, scientists can gain insights into the early history of the solar system. These distant worlds act as time capsules, preserving materials from the era when the planets were still forming. Imagine standing on the surface of one of Neptune's moons, looking out at the Kuiper Belt. The region beyond Neptune is a vast frozen frontier, populated by ancient objects that have remained largely untouched for billions of years. These icy bodies hold the secrets of the solar system's beginnings, waiting to be uncovered by future explorers. Neptune's interactions with the Kuiper Belt also offer clues about exoplanets in other star systems. Ice giants like Neptune are among the most common types of planets found in the galaxy, and their gravitational influence may play a similar role in shaping the structure of exoplanetary systems. By studying Neptune, we can better understand the diversity and dynamics of planetary systems beyond our own. Despite its distance, Neptune's role in the solar system is deeply connected to our own existence. The migrations and interactions of the outer planets help to clear the way for the inner planets, including Earth, to form in a relatively stable environment. Without Neptune's gravitational influence, the solar system might look very different, with fewer planets or a more chaotic arrangement of orbits. Neptune's position as the outermost planet also symbolizes the boundary between the known and the unknown. Beyond Neptune lies the Kuiper belt, the scattered disk, and the Oort cloud, regions filled with mysteries that scientists are only beginning to explore. Neptune serves as a gateway to these distant realms, its presence a reminder of the vastness of our cosmic neighborhood. As we move forward in our exploration of Neptune, its moons, rings, and atmosphere, we are not just studying a single planet, we are unraveling the story of the solar system itself. Neptune's role is one of connection and influence, a distant giant whose gravity shapes the dance of celestial bodies and whose mysteries inspire us to look ever deeper into the universe. Next, we'll explore Neptune's cultural and mythological significance, delving into how this icy giant has captured the imagination of people throughout history. For now, let us appreciate its role in the solar system, a planet on the frontier quietly shaping the world beyond. Neptune is more than just a planet. It is a symbol of humanity's connection to the cosmos, a celestial body that has inspired myths, art, and science. From its name rooted in ancient mythology to its enduring presence in popular culture, Neptune represents the mysteries of the deep, both in the oceans and in the heavens. The planet Neptune takes its name from the Roman god of the sea, a deity who ruled over the vast uncharted waters of Earth. In Roman mythology, Neptune was a powerful figure, often depicted wielding a trident and commanding the waves. This association with water and mystery makes Neptune an apt name for a planet whose vibrant blue hue evokes images of Earth's oceans, even as it drifts in the cold depths of space. Neptune's connection to the sea reflects the human fascination with the unknown. Just as the ancient oceans were seen as a vast, mysterious frontier, Neptune represents the uncharted territories of the solar system. Its distance and remoteness mirror the endless depths of the sea, a realm that humanity has long associated with exploration and discovery. Before its official naming, Neptune was known simply as the planet beyond Uranus, a distant world that defied direct observation. When it was discovered in 1846, its name was chosen to honor both its position in the sky and its striking color, reminiscent of the deep azure seas. The choice of Neptune also continued a tradition of naming planets after Roman gods, creating a sense of continuity and connection with the celestial order. But Neptune's mythological significance goes beyond its name. The god Neptune, like his Greek counterpart Poseidon, was a figure of duality, both protector and destroyer. He could calm the seas to aid sailors or unleash storms that brought destruction. This duality mirrors the characteristics of the planet itself. While Neptune's blue exterior suggests calm and serenity, its interior is a realm of extremes, with powerful winds and storms raging beneath its tranquil facade. In literature and art, Neptune has often been a symbol of the unknown. Poets and writers have used the planet to evoke feelings of distance, mystery, and the desire to explore. Its remote position in the solar system makes it a metaphor for the limits of human knowledge and the drive to push beyond those limits. In modern times, Neptune has also found a place in popular culture. It has appeared in science fiction as a gateway to the outer reaches of the galaxy, a frontier planet where explorers confront the challenges of deep space. From novels to films, Neptune's mystique continues to captivate imaginations, serving as a reminder of humanity's enduring fascination with the cosmos. Astrologically, Neptune is associated with dreams, intuition, and the subconscious. In Western astrology, the planet is thought to influence creativity, spirituality, and the boundaries between reality and illusion. Its role as a symbol of transcendence and imagination reflects its physical position at the edge of the solar system, a place where the known world gives way to the unknown. Beyond its cultural and mythological significance, Neptune also holds a special place in the history of science. Its discovery was a triumph of human ingenuity, a testament to our ability to uncover hidden truths through mathematics and observation. This achievement has cemented Neptune's legacy as a symbol of discovery, inspiring generations of astronomers and scientists to continue exploring the cosmos. Imagine standing beneath a night sky, looking up at the stars, and knowing that Neptune is out there, orbiting in the vastness of space. Its name carries the weight of centuries of myth and meaning, a reminder of our connection to the universe and the stories we tell to understand our place within it. As we move forward in our exploration of Neptune, its scientific mysteries intertwine with its cultural legacy, creating a portrait of a planet that is as much a part of human imagination as it is of physical reality. In Neptune, we see the unending desire to explore, to understand, and to dream. Next, we'll delve into how Neptune compares to other planets, particularly its closest sibling, Uranus, and the lessons we can learn from studying these two icy giants side by side. For now, let us reflect on the cultural and mythological significance of Neptune, a planet that continues to inspire and captivate, even from the farthest reaches of our solar system. Neptune stands as a unique world, yet its story is deeply intertwined with that of its closest sibling, Uranus. Together, these two ice giants form a distinct category of planets, setting themselves apart from the gas giants Jupiter and Saturn, and the rocky inner planets like Earth and Mars. By comparing Neptune to these other worlds, we can better understand its place in the solar system and the forces that shaped it. Let us begin with Uranus, the planet most similar to Neptune in size, composition, and distance from the Sun. Both are classified as ice giants, with interiors dominated by water, ammonia, and methane, rather than the hydrogen and helium found in gas giants like Jupiter. Their blue hues are caused by methane in their atmospheres, yet Neptune's color is noticeably deeper and more vibrant. Scientists suspect this difference may be due to an unknown component in Neptune's atmosphere or variations in its cloud structure. While Uranus and Neptune share many similarities, their differences are striking. Uranus rotates on its side, with an axial tilt of 98 degrees, causing its poles to face the Sun during parts of its orbit. This extreme tilt results in unusual seasons, with one hemisphere experiencing 42 years of continuous sunlight, followed by 42 years of darkness. Neptune, by contrast, has a more typical axial tilt of 28 degrees, similar to Earth's, leading to more familiar seasonal variations. Neptune's atmosphere is far more dynamic than Uranus's. While Uranus appears relatively featureless, Neptune is alive with activity. Powerful winds, the fastest in the solar system, sweep across the planet, fueling massive storms like the Great Dark Spot. Uranus, on the other hand, has a calmer atmosphere, with winds that are slower and less chaotic. This contrast suggests that Neptune's internal heat plays a significant role in driving its atmospheric dynamics, as Neptune radiates more than twice as much heat as it receives from the Sun, whereas Uranus's internal heat is surprisingly weak. When compared to the gas giants Jupiter and Saturn, Neptune's differences become even more apparent. Jupiter, the largest planet in the solar system, is a swirling world of hydrogen and helium, with storms like the Great Red Spot that have persisted for centuries. Saturn, known for its iconic rings, is similarly composed of light gases and has a distinct yellowish hue due to ammonia clouds. Neptune, with its icy composition and vibrant blue color, is smaller, denser, and uniquely structured. One key distinction between Neptune and the gas giants lies in their formation. Jupiter and Saturn likely formed quickly in the early solar system, accreting large amounts of hydrogen and helium from the surrounding disk of gas and dust. Neptune and Uranus, however, formed in a region farther from the Sun, where lighter gases were less abundant. As a result, they are composed of heavier elements, giving them their characteristic icy interiors. This difference in composition also affects their magnetospheres. Neptune's magnetic field is tilted by 47 degrees relative to its rotational axis and offset from the planet's center, creating an asymmetrical and lopsided structure. Jupiter's and Saturn's magnetic fields, while powerful, are more aligned with their axes, reflecting the uniformity of their interiors. Uranus's magnetic field is similarly tilted, suggesting that the ice giants share unique interior dynamics not seen in the gas giants. Beyond the outer planets, Neptune's characteristics set it apart from the rocky inner planets as well. Earth, Mars, Venus, and Mercury are composed of silicate rock and metal, with solid surfaces and thin atmospheres. Neptune, in contrast, has no solid surface. Its visible surface is the top of its atmosphere, which transitions into a thick, slushy mantle of ice and gas. This fundamental difference highlights the diversity of planetary types within our solar system. Neptune also differs in its relationship with its moons. While Jupiter and Saturn are orbited by dozens of moons, including large ones like Europa and Titan, Neptune's most prominent moon is Triton, a captured object with a retrograde orbit. Triton's icy surface and geologic activity make it one of the most intriguing moons in the solar system, offering clues about the processes that shape icy worlds beyond Neptune. In comparing Neptune to other planets, it becomes clear that the ice giant is a world of extremes: fierce winds, mysterious internal heat, and a unique magnetic field set it apart from both its sibling Uranus and the gas giants. These differences provide valuable insights into the diversity of planetary systems, both within our own solar system and beyond. Neptune's unique characteristics also challenge our understanding of exoplanets. Many of the planets discovered orbiting other stars are similar in size and mass to Neptune, suggesting that ice giants may be among the most common types of planets in the galaxy. By studying Neptune, scientists can refine their models of these distant worlds, shedding light on their formation, composition, and potential habitability. Imagine looking at Neptune from afar, alongside its neighbors. Its vibrant blue stands out against the muted colors of Uranus and the golden tones of Saturn. It is a reminder of the variety and complexity of the solar system, a place where no two planets are alike, yet all are connected by the shared forces that shaped them. As we continue our journey, we'll reflect on Neptune's broader significance, both as a scientific frontier and a symbol of humanity's quest for knowledge. For now, let us marvel at its place among the planets, a world of mystery and contrast, waiting to reveal its secrets. Neptune is a world of profound mystery, beauty, and extremes. As the farthest planet from the Sun, it serves as a sentinel at the edge of our solar system, a guardian of secrets waiting to be revealed. Its vibrant blue hues, raging winds, and enigmatic storms stand as a testament to the power and complexity of the cosmos. Neptune's story is one of discovery and wonder. From its prediction through mathematics to its confirmation through observation, Neptune challenged the limits of human ingenuity. Its discovery in 1846 was not only a triumph of science, but also a glimpse into the potential of our species to uncover the unseen. Today, Neptune continues to inspire, serving as a beacon of exploration in the outer reaches of the solar system. But what we know about Neptune is only the beginning. The fleeting visit of Voyager 2 in 1989 provided our first close-up view, unveiling a dynamic world of storms, rings, and moons. Yet this brief encounter left us with more questions than answers. What drives Neptune's ferocious winds, the fastest in the solar system? How does its internal heat sustain its weather systems? What lies beneath its icy mantle? And could there be conditions suitable for life on its enigmatic moon, Triton? Neptune also holds a unique place in the grand narrative of the solar system. Its gravitational influence shaped the orbits of distant objects in the Kuiper belt and scattered disk, helping to sculpt the outer regions of our cosmic neighborhood. It serves as a bridge to the unknown, a gateway to the uncharted territories beyond its orbit. Imagine standing on one of Neptune's moons, gazing out at the planet itself. Its azure color glows faintly under the dim light of the distant sun, a serene yet powerful presence in the cold void of space. This image captures Neptune's duality, a planet that is both calm and chaotic, inviting and mysterious. Neptune's significance extends beyond our solar system. Ice giants like Neptune are among the most common types of planets discovered in the galaxy, offering clues about the formation of planetary systems around other stars. By studying Neptune, we are not just exploring a distant world. We are gaining insights into the diversity of planets across the universe and the forces that shape them. In mythology, Neptune was the god of the sea, a realm of endless depth and untold secrets. In many ways, the planet that bears his name lives up to this legacy. Its distance and complexity remind us that there is still so much to learn, even within our own solar system. Neptune challenges us to push the boundaries of exploration, to build the technologies and missions that will one day return to this icy giant and uncover its secrets. As we reflect on Neptune's story, we are reminded of humanity's unyielding curiosity and drive to explore. Neptune is a symbol of the unknown, a distant world that calls us to look beyond the horizon and ask the big questions about our place in the universe. Let us dream of the day when we return to Neptune, when new missions equipped with advanced technologies can dive deeper into its atmosphere, orbit its rings, and land on its moons. Imagine the discoveries waiting to be made, discoveries that could redefine our understanding of planets, both within our solar system and beyond. Neptune is not just a planet at the edge of the solar system. It is a frontier, a reminder of how much there is left to explore and learn. It stands as a testament to the endless possibilities of science and the enduring power of human imagination. As we conclude this journey through Neptune's story, let us carry its lessons forward: the importance of curiosity, the value of exploration, and the wonder of looking up at the stars and dreaming of what lies beyond.